and welcome, and sorry I'm a couple of minutes late because my internet just went down the moment I was about to start streaming, so what a fuss. Anyway, we're sorted, we're ready now, and this is the third in 3 of the live streams in this series. This is the AQA GCSE Physics Paper 1 mock exam live stream, and today I'm going to talk about explain and describe questions, and I'm going to talk about the particle, model of matter and atomic structure. So they're two of the units that are in AQA Paper 1, and most students here will be doing AQA Paper 1 in their mock exam. And well, we're going to talk about how to practice and how to do those questions, and if there's time at the end, then we'll do a little bit of Q&A. If you have any questions, pop them in the chat at any point at all during the whole stream. If you're watching this recorded, then hello future, how did the rest of the pandemic go? But if you have any questions, then do pop them in the chat, because they're the types of things that I will develop into future video ideas, or even I'll be there to answer them in the comments as well. So that's what we're covering today. The previous 2 live streams, they covered all of this stuff. They covered practical questions. Well, I talked about how to revise first of all, and we covered practical questions, and we did a little bit of Q&A at the end of that as well. And then the last live stream was about calculation questions. So look back at these, they're really useful. I think preparing you for your mock exams. Mock exams are so important. You know, doing assessments is so important. I know that it's quite onerous, but actually getting to know what you do and don't know, and for your teachers to know what you do and don't know, is really important for developing you on your way, so you can be most confident going into the terminal exams. So in that previous calculation live stream, I did energy and electricity, because there tends to be a lot of questions about energy and electricity in those. This stream is sponsored by Tassomai, and thank you very much to them for sponsoring this video. We really like Tassomai in our school, because it's a quizzing app that is based on evidence of how students learn best, and it's used in schools and by private subscribers. You can check it out at tassomai.com at any point, and feel free to ask any questions as well about Tassomai if you're not sure. Tassomai uses 3 of the top 5 revision techniques, and I go through those in the first live stream in this series, and it makes sure therefore that your revision is fast and effective, and I think that's really important when you've got a lot of subjects to revise. It makes sure that you're doing practice quizzing, and it uses an AI algorithm to actually select the right questions for you at the right time. It makes sure you're doing space revision and interleaves your topics for you, and those are the best revision techniques. All you have to do is about 10 minutes a day, 4 times a week, to get your daily goals, and the more you do that Tassomai, the better your memory will get. What's more, you can use Tassomai to identify your key priority areas, and then you can target them with the 2 other revision techniques that the evidence recommends, and that's self-explanation and elaborate interrogation. And actually, self-explanation is really the process I'm going to talk about a lot in this video, which is decoding, plan, answering and check, and working through this kind of technique, working through one step at a time how to answer each individual question. And the more you do of this, the better, the stronger you will get, and the more confident, the easier you will find those exam questions. So I strongly recommend that you work through in this step-by-step way that I'm going to talk through these today. Yeah, hello Abdullah, maths tutoring. Yes, you can use Tassomai for GCSE maths. They do have GCSE maths, and they do have English as well. Okay, so decode. That means what is the question asking you to do? And that's the first step to do. I say you don't read an exam question, you decode it. You figure out, what are you expected to do? What have you been told to do? And I strongly suggest you stick to just underlining the command words. And then decide what kind of branch of physics is this question actually on. What part of your syllabus is this question actually all about? And that will kind of narrow down your thinking, and you bring to mind all the important parts, all the important things that you need to state in that kind of area of physics. Think about theories, think about laws, the big important things that your teacher will have actually put forward that you can apply to the question. Then read the full question and do it carefully, looking out for any other modifiers like not or other or increase or decrease. I've lost track of the number of times I've marked an answer which is all about something increasing when the question asked you about something decreasing. So read really carefully. Then plan, and this is the most important thing, and the most important thing for written questions especially is think before you write. Think before you write. I cannot stress that enough, because there's so many people that start writing and it's clear that as they're writing, they're thinking. And the more you get used to this, actually think about what you're going to write before you write it down, the stronger that answer is going to be. So ask yourself, will any diagrams help? Are there any equations to apply? That sounds a bit funny, but in physics, a lot of our written questions actually are about equations. You know, if we know speed is distance over time, and you've been told the time it does the same thing in a shorter time, then the speed's going to be bigger. Okay, so you can use equations to write written answers, if that makes sense. Whatever you do, think before you write. Look at the number of marks and the clues in the question to kind of imagine what's going to be on the mark scheme, and I'll talk to you a bit about that today. Then actually write the answer. That's the third step. And as you're writing, because you've had that time to think, you'll improve the response as you write. So as you write, you'll think, oh, actually, I'll put this word in there. Or actually, I remember that detailed bit that I need to get into there. And you can actually use bullet points, and bullet points are really especially useful to you when you're writing your answers in written questions, because it will keep track of the number of separate things you've said. Even in a quality of written communication, even in a 6-mark level of response question, you can use bullet points. Lots of people are surprised because their teachers have told them maybe to write in full sentences. Yes, write in sentences, but use bullet points to keep track of them. Okay, it is okay to do that. It's good, actually. It makes it easier to mark as an examiner. And then lastly, check. And I think this is the most important of any answer. Check your answer. Check you've done everything you've been asked to do. Remember at the start we underlined the command words. Well, the command words are the commands. They're the things you've been asked to do. So actually make sure you've done everything that you've been told to do. There is a command word for every mark on an exam paper. And then lastly, check you've answered the specific question. So was it increase? Was it decrease? Was it actually the question that you've been asked that you've answered? Have you gone off on one about something completely related, but not that answers this specific question? Then actually reread and upgrade your language. So lots of people use this like missing word mark, just to add in another word above that. It's totally okay to do that. You don't need to. The exam response doesn't need to be neat. It just needs to be legible. Okay, work through that in every single step, and what you're going to get in this live stream is you're going to get decode, plan, answer, check to remind you on the side of the example questions. And what we're going to do is we're going to work through that thinking on every single question we tackle today to show you how you're going to actually decode, how you're going to plan, how you're going to actually write your answer, and how you're going to check back at the end. So bear with me, and I hope it'll be really, really useful to you all. Thank you very much, Mahima. Lovely to have you on the live stream. This live stream is sponsored by Tassamai, another word from them. Thank you so much for sponsoring this revision live stream. Tassamai is the scientific way to learn, okay? And as a head of science, that really appeals to me. So check out the links in the description or the pinned comment to find out more. And one feature of Tassamai is this tree, and your tree grows as you use Tassamai through the branches, which are the branches of each course, to the leaves, which represent the individual learning objectives. You can really quickly identify your priorities. So your priorities are the red or the amber leaves. And then you can target them with really focused revision. And Tassamai has courses for each of the major exam boards in GCSE Sciences, English Literature and Maths. And we know that by getting your daily goals on Tassamai, you'll catch up and you'll remember all of the key knowledge, and there'll be no gaps when it comes to those exams. And find the link in the description to find out more. And that's a key bit that I've just said there about catch up, because I know we've all been through quite quite a few moments. Yeah, it's been a minute. It's been a bit of a time in schools, or really out of schools, and it's been a bit tricky. And so something like Tassamai that can help you identify your gaps is really, really useful. I'm going to talk to you about how we make exam questions hard, right? We're going to talk to you about what we call cognitive load theory. In the chat or in the comments, like, tell me, do your teachers actually talk about cognitive load theory to you in lessons? I'd be really interested to know. And this is about the way that examiners make questions hard, okay? So I first of all, I'd encourage you to think about an exam question as not really a question at all, but as a problem to be solved. And you have to get information to solve that problem from two places: from your long-term memory, and that's information from your head, stuff that you remember, and your sensory memory, which is like the stuff that is actually information given to you in the question. And you need to take those two bits of information and load them up into your working memory. And your working memory is the stuff that you're thinking about at that specific moment. And so here they come, here's the things being loaded up. An easier question would maybe just have two things loaded up into the working memory to solve that problem. A harder question might have four things loaded up into that working memory. So cognitive load theory says that when something gets hard, it's because you're having to think about more things at once. Okay, and to do that stuff you're thinking about right then, if it gets overloaded because we think there's only limited space there, then we can find that really tricky. But you use those bits of information to solve the problems in the question. And well, there is something really very useful. You use those bits of information to actually come to a solution. And the good thing is, the good news is, we think that actually the long-term memory is basically infinite. Okay? It has no limits. We think the long-term memory, you can stuff more and more and more information into that long-term memory, and that's really good news. So the way to limit the cognitive load, the way to make things easier in an exam, is to actually be able to move things from this long-term memory quicker and faster into the working memory to solve problems. So that is why something like retrieval practice is such a good exam technique. It's because the more you have in that long-term memory, the quicker you're going to bring them up, the quicker you're going to bring those things to mind to solve the problem. So think very carefully about this point here, where you're actually trying to solve the problem. That is what the exam technique is can you get information from those two places, your brain and the exam paper, that's the sensory memory, the stuff they've actually told you in the question. Can you get those two things ready to solve that problem quickly? That's a good tip. Okay, that's what that is. There's an example of a high load question. Now, if you just have a little look through this with me, first of all, to solve this question, you have to remember the equation for distance is speed times time. So you have to get that one bit of information loaded up from your brain into your working memory. Next, you have to look into the question and find the times. In this case, this is about using radar location to actually work out the distances to planets. You have to get the times ready from the question, that's from the sensory memory. And then you have to remember to convert those times, which are in hours, convert them into seconds. And then you have to get the information, which is the speed of light. They've told you that there. And you have to remember to, once you've calculated the distance, to divide that distance by 2, because the wave has gone there and back. And then you have to actually do the calculation 3 times and do it accurately. So those are the reasons. That is a reason why something is a high cognitive load question, because you're having to think about all of those 4 things at once. Okay, going to crack on with the actual content in just a moment. Just to say one more time, thank you to Tassamai for sponsoring this revision live stream. And Tassamai is the scientific way to learn, and that really appeals to me as a head of science. Feel free to ask questions in the Q&A later. Tassamai uses AI to target the areas you need to develop in order to master the content of your GCSEs. Tassamai gets to know you, and it makes sure you keep practicing your priority areas until you can't get it wrong. And that's the idea, really. Practicing something until, not just until you know it or you understand it, but until you can't make a mistake. And I use Tassamai in my school to make sure that students have memorized the key content for their exams, and we trust it because it's based on the science of how people learn. And we know we can rely on our students who complete just 10 minutes of Tassamai 4 days a week to get all of the recall questions and remember all of the key facts to help them lower the cognitive load of the harder questions. You might get Tassamai through your school, but if not, you can always sign up a private subscription on the website, and there's a 7-day free trial, and I strongly suggest that you actually give that 7-day free trial a go, ready for this set of mock exams. Find the link in the description or go to www.tassamai.com to find out more. So as I said, we're going to talk about the particle model, and we're going to talk about the atomic structure and do some questions on those. So a little bit of detail first. Firstly, the definition of what the particle model. It's a massively successful model that actually explains the behaviours of solid, liquids and gases. Sometimes we call it the kinetic theory, because it really talks about molecules having different amounts of force of attraction between them, the highest forces of attraction being in a solid, and the most energy being in the gas. So really kinetic theory or particle model is all about the tussle between this kinetic energy of those particles trying to get away from each other and the force that's kind of holding them together in place. And we call some terminology we use. We call the change of state between solid and liquid fusion. Doesn't matter which direction it goes, you can call it fusion. And between liquid and gas, we can call it vaporization. And that will be used in calculations as well. So here's our first exam question. And the first thing we're going to do is going to decode this exam question, this written exam question. First of all, look for the command words. This is a describe question. So we don't have to do an explaining, we just need to say what it is like, rather than why it is like it is. And understanding command words and what they specifically mean in exam questions is really very useful. And the simplest ones are describe versus explain. Describe is what is it like, explain is why is it like it is. So there's no point in us telling anything about why something is like it is. This one is just after an explain. So now let's read during melting, the particles of a substance change in their arrangement and their motion. And it's worth 2 marks. So I'm thinking now in this planning step, I'm thinking to myself, well, how many things am I going to need to say? 2 things. And they've given me some clues as to what those 2 things are. There's going to be a mark for the change in the arrangement, and there's going to be a mark for the change in the motion. Okay, now there's one more thing I need to be aware of in this to load up into my working memory. This is talking about melting. So that's the change from a solid to a liquid. So what's the change when the particles change from a solid arrangement to a liquid arrangement? Well, in a solid, they have changed from fixed in a, fixed is going to be the motion in a moment. They've changed from a regular arrangement to randomly arranged. But importantly, still touching. Okay, in a liquid, particles don't get a lot of distance apart. That's the first mark dealt with. The second mark, as we've decided already, is going to be about the motion. So now we're doing this answer check. And did you notice how I added something there as I was thinking? What is a motion difference? Well, they were in fixed, so from fixed, vibrating on the spot, to now able to change places. We sometimes describe that as like sliding over each other in a liquid. Okay, so they are touching, but they're changing places. And now the last step is check. Have we done everything we've asked to do in the question? We've asked to describe these changes, and the changes we've been asked for is the arrangement and their motion. So yes, we have done everything in the question. The next example is actually about specific latent heat, and a bit more about that change of state. Specific latent heat is the energy required for a change of state of 1 kilogram of a material. And importantly, during a change of state, the temperature of a substance doesn't increase. And why is that? This is because the average kinetic energy of the particles doesn't increase, and temperature is proportional to average kinetic energy of the particles. But you could say it is the average kinetic energy of the particles if you like. However, the internal energy does increase. Okay, but internal energy is made up of 2 things. It's made of the kinetic energy of the particles, and it is made of the potential energy of the particles. So actually, in a change of state, the energy goes into changing the potential energy of the particles rather than the average kinetic energy. So when you think about these graphs here, what we have, if we've got temperature against time, we have the kinetic energy changing when the temperature is rising, the potential energy changing when the temperature is the same. So kinetic energy is changing when temperature is rising, potential energy is changing when the temperature is the same. Kinetic energy is increasing when the temperature is increasing, but during a change of state, the potential energy is the one that changes. So the average kinetic energy of the particles, which is the temperature, isn't changing during those points. Okay, that's the key bit of this from this slide. Let's crack on then. Oh look, during a change of state, that's some information they've given you. First of all, we're decoding. the temperature of a substance doesn't change. So they've told us that. We're not going to get any marks for saying anything about that. We got to explain why. So now we have to say why it is like that is. So what is really going on during that change of state? Oh, incidentally, this would be a 2-mark question. So why is it that the temperature does not change? So we know that we're going to be increasing the energy or decreasing the energy, it doesn't really matter which way, but let's just say we're increasing the energy in the thing, we're increasing its internal energy. This question is about internal energy. So during a change of state, why doesn't the temperature change? That is because the kinetic energy stays the same. And as I've actually thought this through, now I'm answering, I can add something in there. The kinetic energy of the particles stays the same. Okay, so this has shown the examiner that you know that the temperature is linked to the kinetic energy of those particles. What does change though? Okay, the potential energy changes during a change of state. The energy goes to causes the potential energy of the particles to change. And once more, let's check back through. Have we done everything we've been expected to do? Yes, we've explained. We've said why something has happened. They told us that the temperature doesn't change. Not going to get a mark for that then. But what we are going to get marks for is explaining why that is the case. Okay. Now on to the particle model and pressure. And this is an animation here of Brownian motion, which is just the random motion of particles of a gas. Now when we're talking about gas pressure, we always talk not about the collisions between the particles, and the particles do collide, but we'll save that bit for explaining reaction rates in chemistry, please. Okay, when we're talking about gas pressure in physics, we're really just talking about collisions with the container. Okay, so there's two things you're going to get when you get higher pressure. When you increase, let's say, the temperature of that gas, then they're going to move around quicker, so we're going to have more frequent collisions with the container. That's a higher pressure. Also, we're going to have a higher force, or you could say a higher speed of collisions with the container. So those two things, they are the things that change when a gas pressure changes. And it's a really common mistake to make to talk about collisions between the particles. Yes, a higher pressure does have collisions between the particles, more frequent collisions between the particles, but that is explaining why a reaction rate is affected by pressure, rather than explaining in physics why the actual pressure itself is changing. Okay, so let's have a little decode of this. This is an explain question. Look, when the temperature of a gas increases, the kinetic energy of the particles also increases. So how does this change the temperature? How does this change in temperature affect the pressure of the gas? Explain your answer. Now this one is a 3-mark question. So actually there's several different things you're expected to do here. First of all, there's a 1 mark, and this is just a AO1, a bit of recall. How does temperature affect pressure? So it's told you that the kinetic energy is increased, the temperature increases, so higher temperature. I've kind of skipped ahead, haven't I? We planned it when we looked at what the different marks might be. Now we're on the answer things. Higher temperature, higher pressure. You could have just written pressure increases here. That would have been good enough. Okay, because they've told you the temperature has increased. How did that change affect the pressure? Then explain your answer. So there's actually 2 marks for this, and that is going to be the higher pressure is caused by more frequent or more often collisions between the particles and container. Okay, so you've got to say this one, you've got to have more frequent or more often, more per second, not just more, and certainly not like they start to collide, but more frequent collisions between the particles and the container, and that these collisions have a higher force or have a higher speed. So particles collide with the container again. Always with the container when you're talking about gas pressure. At higher speeds or with higher force. Okay, so that's gas pressure dealt with. Let's just check we've done everything. Have we said how it affects the pressure of the gas? Yes, we've said higher pressure. Have we explained that? Yes, we've said what a higher gas pressure is. More frequent collisions between the particle and the container. More frequent, higher force collisions between the particle and the container. I hope I've made that point enough now. All right, really quickly then, that's all of the stuff on the particle model we're going to do. Thanks very much to Tassomai for sponsoring this revision live stream. And Tassomai is a quizzing app which is based on evidence. And as a head of science, it really appeals to me when something is based on evidence, okay? Because all of science is obviously based on evidence. And it really helps students get the top grades, which is what we're all about here at GorillaPhysics. So check out the links in the description or go to tassomai.com to find out more. And one of the Tassomai mantras is that practice makes permanent. But what is more is that Tassomai gets to know what you do and don't remember. And I use Tassomai in my school to make sure that students are focused on memorising the key content for the exams. And we trust it because it's based on that evidence. By doing just 10 minutes of Tassomai 4 days a week, you'll ensure you're learning the content the fastest and most effective way possible. And if you don't get Tassomai through your school, you can always set up a private subscription. And I suggest you go for the 7-day free trial. Give it a go for this mock exam series. See how it works for you. And if you like it, then buy it for the real thing. Okay, thanks very much for listening to that. Now we're going to work on the atomic structure or the radioactivity topic, and we're going to do some written questions on that. This is isotopes of the element. These are 3 different isotopes. These are isotopes of helium. This is called helium-3 because it's got a mass number of 3 and it's helium. And this is helium-4, it's got a mass number of 4 and it's helium. And this is helium-5, it's got a mass number of 5 and it's helium. What is it that makes them helium? Well, they all have 2 protons. So the bottom number in the position Z, if you look up here, this is the kind of annotation here. Okay, this bottom number here is always the proton number when we do nuclear notation. So that's what you're looking at down here is nuclear notation describing these 3 different isotopes of the element. And then the thing that's different is the mass number, the top number. Okay, that is the number of protons plus neutrons, the total number of particles in the nucleus. And X, or like He in this case, is the chemical symbol. Okay, and this shows you what is different about isotopes of an element. They all have the same number of protons, that's what makes them helium, and they all have different numbers of neutrons, and that's what makes them isotopes. They are the same, chemically they're exactly the same in fact, but they have different masses. Okay, so this is a straightforward one really, because this type of exam question, when we decode these, we should be thinking we're going to get these nice and quick, state and give. And that just means do you or do you not remember the answer to this question. What is meant first of all by the term isotopes of an element? So isotopes of an element have the same number of protons different numbers of neutrons. So that is just a little bit of AO1 recall, do you or do you not remember your meanings. Now, all in the PowerPoint that I'm going through here and my other videos using these PowerPoints, then I always put in italics the words that you need to memorize the meanings of. Next, give the name of the particle which in the nucleus which has a positive charge. That one is the proton. The particle in the nucleus which has a positive charge. That is the proton. Now that was really straightforward, okay? I didn't do much thinking or planning because that was just do you know it or do you not know it. There are certain numbers of questions which are just pure recall like that. But you should still be thinking and checking back, have I done what I expected to do? This is just a give, this is just a state. Yes, I have answered all of those. Look back at the number of marks, I haven't written them on this one, but check you've done everything you expected to do. I'm going to talk about the development of the model of the atom now just briefly. It started with Democritus, then Dalton, Thomson, Rutherford and Bohr. And this really focuses on the change between Thomson and Rutherford, but we should know the whole story. Democritus, ancient Greek natural philosopher, thought that all matter is made of atoms which are indivisible, can't be divided. Dalton agreed with that, but said that actually not all matter is made of the same atom, so the atoms of oxygen are different to the atoms of carbon, so on and so forth. And he did lots of chemistry and worked out the masses of, for example, carbon dioxide and things like that, and did basically Dalton did all of chemistry. He solved chemistry, he did balancing equations, moles and all that kind of stuff. Thomson, you sometimes talk about Thomson having discovered the electron. He found that a particle in a cathode ray was actually negative and had mass, and so that is what these negative things in this plum pudding model are. He said the atom is a bit like a plum pudding, a bit like a cake, and the cake is the positive stuff, and you can remove these kind of little things that are embedded, like plums, which are the electrons. Rutherford, he found out that actually the atom had a small and incredibly dense positive nucleus, and that that would be orbited by some electrons. I'm going to talk about his evidence in a moment. And then finally we use now the Bohr model, and that's as far as the story goes at GCSE, but it's not as far as it goes in A level or onto university level physics, so look forward to finding out more about the atom in the future. But let's just say that's now the accepted model, the model that we use. It does explain a great deal of physics and chemistry, and essentially all that's added in the Bohr model is a reason for the electrons to stay in their orbits. They have some energy, and so we call that an energy level, rather than an orbital or a shell like they might in chemistry. And that the nucleus itself isn't just positive stuff on its own, it has protons which are positive and neutrons which are neutral. And that's the whole story, But why did those models change? And that's the crux of this topic, really. Models change because evidence changes. We get new evidence that can't be explained by old models, and so we go ahead and change the model. Models are used to explain evidence. They're used as ways that we can explain what's going on in the experimental evidence that we've got in physics. So here is the experiment that Rutherford did to change the plum pudding model into the nuclear model. He actually fired some alpha particles, that's over on this side here, at a piece of very thin gold leaf. That's the thing in the middle there. And he did it in a vacuum chamber, because otherwise those alpha particles would just have collided with other particles in the chamber. And he found, as he was expecting, most of the alpha particles went straight through the gold. Okay, that's what he was expecting. Okay, he was expecting if it was cake, then those alpha particles would just bombard their way straight through. So that's what happened. However, they moved this movable detector because the ones that were on that pathway didn't quite add up to the total that should have been there. So they moved this movable detector back and forth around this side, and they found some of the particles were deflected. That's path 2 here. Some of the particles deflected like so. And they found some of the particles, and then that was a bit surprising. There was actually something that was actually moving that pathway, moving that alpha particle off course, and they found those at particle 2. But even those at path 1 and path 2 did not add up to all of the particles that were being actually emitted from the alpha source and going straight on through. Thanks so much, YOLO Gamer. Yeah, I do remember you actually, and nice to have you still here. But some of them, and this was the surprising thing, actually came back the way they came from. And that was pretty darn amazing, right? And that shocked Rutherford. He actually found, when he moved the particle detector back to the other side, back behind the gold leaf, some of them came back the way they came. And that's where you get that famous phrase that he said, it was as if you shot an artillery shell at a piece of tissue paper and it came back and hit you in the face. Okay, this is a little diagram of what he decided must have been going on then. Most of them were just going through because most of the atom was just empty space. That explains the evidence number 1. And he thought also that there must be some charge if the nucleus, if part of that atom was able to do a force on a positive thing. Okay, so there must be some positive charge somewhere. So there was a sort of central location which had a lot of positive charge, and also that whatever that positive charge was had to have the majority of the mass, because it was able to actually knock an alpha particle back the way it came. So that is how his model explained the evidence. And as I say, when this whole topic is all about when new evidence arises which cannot be explained by the old model, scientists either get rid of the old model and come up with a new one, or they change the model. Okay, so really this is a story about evidence and knowing that from Dalton to Thomson, he looked at the cathode ray tubes, looked at electrons. From Thomson to Rutherford, that was the alpha particle scattering experiment which I've just described. And from Rutherford to Bohr, they actually needed some way to explain why the electrons didn't just spiral in and destroy themselves on the nucleus. So he talked about the electrons having energy. And also there was Chadwick who did some experiments to discover the neutron. And now we have the Bohr model that we use today. Remember, evidence changes models. And all of that to get answers like you'll see in a moment. You don't need to describe Chadwick or Bohr's evidence is something that's important to remember. Okay, so scientists currently use the Bohr model to explain many behaviors of the elements, and this model is accepted by the scientific community. Suggests the reason that scientists might change the accepted model of the atom. All you're looking for here, again, it's a 1 mark, although it is quite a tricky thing. Suggest, okay, means there might be more than one way to state this answer. This is our decode step. Suggest. Then plan, recall that to mind. What was that whole topic about? Right, hang on a minute, let me think. It's about models, it's about the Bohr model, why it's accepted, why we might have to change a model. All right, okay, I remember this. This is about evidence changes models. So why might they actually get rid of an old model? Okay, this is maybe new evidence might be found. Okay, new evidence arises, new evidence, new experiments are conducted, anything like that. New data, anything like that. New evidence is found which cannot be explained by the old model. Okay, let's just check. Have we come up with a reason? Yes, that is the reason. That is the crux of this whole bit here. Now, just to go a little bit further on that kind of thing here, because you will be thinking to yourself, that's a lot of detail. Surely I'm not going to learn all that detail just to be able to say that. Yes, this is a common one for like a describe-ish 6-mark question. So let's have a go at this one. Decode first. What do we actually have to do first of all? Whenever I get a bit bumped like that, I always think to myself, what do I need to do here? Because when I'm reading, then I'm thinking about that. So I have to name some. I have to name the model Rutherford proposed to explain their evidence, and I have to describe the evidence which led to the scientists changing the accepted model of the atom. Okay, so this is about that story of the models of the atom. Which bits do I need to explain? Do I need to go into any detail about Democritus or Dalton? No, I don't. Do I need to talk about Bohr model? No, I don't. So I just need to get from the plum pudding to the nuclear model. And then now let's have a little read. Before the year 1911, scientists used the plum pudding model of the atom to explain the evidence that they had. In the year 1911, Rutherford, Geiger, and Marsden completed an experiment, they haven't told me the name because I've got to name it, which gave new evidence and changed the model. So now we're going to plan. Now this is a 6-mark question, it's crucial. There's always going to be, or normally going to be, 2 different parts. Okay, the first part is going to be naming the model, okay, and second part is going to be describing the evidence. So really you could think about it as being 2 different questions within that 6-mark question. Okay, so I'm going to answer it in that order. First of all, I'm going to talk about the model, and then I'm going to talk about describing that evidence. So first of all, the model that Rutherford proposed. So Rutherford proposed, literally you could actually just write the nuclear model, but why not try writing bullet points but writing sentences? The nuclear model of the atom. Okay, what's next? Now I need to describe the evidence that led them to propose that. What was the name of that thing we've just done? It was the alpha particle scattering experiment. So something we'll be looking out as examiners for, the alpha particle scattering. It's sometimes called, incidentally, the gold leaf experiment or something like that. Rutherford scattering is also acceptable. Okay, that is the name of that bit of evidence. Okay, that is the evidence. Now we need to describe more about the evidence. We don't need to explain how that led to the model, though, did we? We just need to describe the evidence. So let's go through it. What actually happened then? So alpha particle scattering, most of the alpha particles went straight through. This leads to us knowing that the atom is mostly empty space. Okay, now some alpha particles were repelled and some through large angles as well, but let's just go for some particles repelled, and this leads to there being a nucleus with positive charge and most of the mass. Okay, now let's check. Have we done enough here? Have we done enough for 6 marks in this question? Yeah, we've got the name of the model that he proposed, and we've got the name of the alpha particle scattering. Let's keep track of this too. Then we've got most of the alpha particles went straight through. That's the description of the evidence. That shows that the atom is mostly empty space. That's that. Then next one, some particles are repelled, and lastly, that means that there must be a positive charge and most of the mass. So we've also described that model as well in there as well. So I think possibly this question should have had name and describe. That would have been a bit more valid for what I've written there. But there we are. That is a 6 mark question. And that's how we decode, plan, answer, and check back with it. Okay, next one then we're talking about the 4 different types of decay, if you like: alpha, beta, gamma, and the neutron emission. We need to just talk about their penetration power and their ionizing ability, and those are the 2 things. Don't get bogged down in like which is the most dangerous or anything like that. Like basically, some of them can go further more through things, and some of them can do more damage when they get there. They can do more ionizing when they get there, and actually it's because they are more or less ionizing that they are more or less penetrating. This table goes through what they all are as well, and an alpha is a helium nucleus. The black bits are what they all are. Beta is a high-speed electron. Gamma is a photon of high-frequency electromagnetic radiation. Now, neutron emission just means that a nucleus can just get rid of a neutron, and that can make the neutron more stable. You don't need to know any more detail about that. All the codes there as well that you need to memorize when you're doing balancing nuclear equations. Let's talk about what they are like then. The alpha is the most ionizing, and the gamma is the least ionizing, and but the alpha is the least penetrating, and the gamma is the most penetrating. And we talk about that alpha is stopped by just 2 to 4 centimeters of air. Beta has about a range of about 2 meters in air, and gamma's range is almost infinite in air. You need thick lead or concrete to absorb it. Okay, let's decode this one then. A teacher is demonstrating with the source of radiation in the lab. They say this. Explain why this is true. Right. So this is a source of alpha and beta radiation. This is what the teacher says to the class. Please stand at least 2 meters back from the demonstration. Explain why they say this. Okay, let's think about it. Why would you want somebody to be 2 meters back? Oh, I remember, this might well be about the range of alpha and beta in air, mightn't it? Okay. And you're told in the question, look for the clues. It's an alpha and beta emitter. It's a source of alpha and beta radiation. Why would you be told to stand at least 2 meters back? Well, first point, let's start answering now. We can do this. Alpha has a range of only 2 to 4 centimeters. Okay, and beta, let's go for that as a second point, has a range of 2 meters. So none of those particles will get through the air beyond 2 meters, and so by being at least 2 meters back from the demonstration, then none of those particles are likely to hit the people. And so the last point is that basically. And when you're further than 2 meters, those particles will not be able to reach the people. But importantly for this one, what we'd really like to read is that the radiation levels will be back to basically background levels, background radiation levels. So radiation levels okay, and background level is a really important thing to think about when you're talking about safety, because even that person doing that demonstration will only have a small increase in their kind of daily radiation dose. Now, contamination and irradiation. Now, there's a big distinction to make. Contamination is the worst one, because if something gets contaminated, it will actually get some radioactive material on it, i.e. some actual nuclei which are radioactive. And therefore it will continue to be a source of radiation once the source is removed. Whereas an irradiated material, if I irradiate something, it's being bombarded by the alpha, beta and gamma. So we say it's been exposed to radioactive particles. However, excuse me. However, it does not become a source when you remove the irradiating source. So the important thing to remember is contaminated objects become radioactive, irradiated objects do not become radioactive. They do not become a source. And we need to talk about precautions and risks, but appropriate ones. So let's decode this. Explain why this doesn't pose a health risk. A student finds out that fruit in the supermarket is irradiated before being sold. Now, how have they made this one a little bit harder than just asking you what's meant by the term irradiation? Well, they've increased the cognitive load because they've said, well, it's actually about fruit in a supermarket. And you might think to yourself, I don't know anything about fruit in the supermarket, that's not in the course. You're right, it isn't in the course. But what is in the course is understanding that irradiated objects don't become radioactive once the source is removed. So let's answer this. So first of all, irradiated means exposed to radioactive particles. Okay, that's essentially just the definition of irradiation. So now all we need to do is just apply it to our situation here. So therefore, you don't need to say therefore incidentally, the fruit does not become a source of radiation. Okay, it's that simple. It's just really, they could have just said, explain what is meant by irradiation and why an irradiated object isn't a hazard. But instead of doing that, they've given you in a bit of a context, and that can sometimes trip people up. All right, fission and fusion then, just to finish this off. Well done those of you that have stuck around. If you do have any questions, then stick them in the chat and I will talk briefly at the end. So fission is basically when a more massive, unstable nuclei decays to become a less massive, more stable nuclei, and energy is released. Okay, so this is a large nucleus decaying, splitting to become a pair of smaller nuclei. Now, importantly, these neutrons are emitted, and they go on to cause more fissions. So fission happens when a neutron is absorbed by a fissile nucleus. Large unstable nucleus. So the thing about this is that those neutrons are emitted, so this is the large nuclei splits into the smaller ones. Also some neutrons are emitted. Those neutrons, they hit other large nuclei which split into smaller ones, which release more neutrons, and so on and so forth, and you get this chain, and we call that chain a chain reaction. Okay, there we are. basically, as you go through this, then the particles have a lot of kinetic energy, and that can do a lot of damage. We control this. This is what we use in a nuclear reactor. We control this by absorbing the neutrons, because if you absorb these neutrons here, yeah, they don't go on to cause more fissions, so you don't get a chain reaction. If we want to just make an explosion, which apparently sometimes we do, then you know, go into the ethics of that another time, shall we? But the if we want to make an explosion, then we just let it happen. We just let that chain reaction get out of control. Okay, now fusion is the opposite to that. It's when lighter nuclei, smaller nuclei, less massive nuclei fuse or join to create a more massive nuclei. So here's our sort of starting points. These are two isotopes of hydrogen, tritium and deuterium. Could be any light nuclei, incidentally, but this is the example that we use, and this is what we use when we want to make a fusion explosion or want to do fusion in the lab. And a lot of energy is released. Gamma radiation is what that energy is in the form of. You get very high speed neutrons, which also do damage, and helium. And so if we describe that, I think I've described that in an equation. Yes, I have. Yeah, this is the deuterium plus the tritium makes the helium and a neutron. Okay. Now we can't speed that up or slow it down, but the nice thing about that is there's a limiting factor, and that's the amount of hydrogen that you had in the start point. And the reason why you need a lot of energy to get that going is because you need a lot of energy to force those two hydrogens, which want to repel each other because they're both positive, and you need a lot of energy to make them actually occupy the same space and so fuse. So let's describe the process of nuclear fission. So this is describe, decode. It's fission we're talking about, so we can forget everything about fusion so far. And in our answer, we're going to explain what is meant by a chain reaction. Okay. So let's describe the process of nuclear fission. That's our first part, and then we're also going to need to remember to explain what is meant by a chain reaction. That's our plan. Answering it. What happens is a massive nucleus, we're just looking for in this first bit though, absorbs a neutron. Right, okay, it splits. Okay, that is the next thing, the next second point. Large nuclei splits, or splits really. Okay. The large nuclei splits into two or more fragments. What is left over, you get daughter nuclei, or smaller nuclei, less massive. Can you see how, because I've thought it through, I'm upgrading my language as I actually write. Daughter or less massive nuclei, and you need both things for this mark, and neutrons. Okay, we say 2 or 3 neutrons, but importantly you need to say we've got neutrons being released, and those neutrons go on to cause further fissions. Now, have we done everything? Let's check. Have we done everything in this? We've described the process of fission. That's the first 3 actually. Massive nuclei absorbs a neutron, large nucleus splits, daughter or less massive nuclei, and 2 or 3 neutrons are released. Okay. Have we explained what's meant by a chain reaction? Well, yes we have. The neutrons go on to cause more fissions. That's the chain reaction. You might want to cover yourself here by just saying, well, that is what a chain reaction. This is a chain reaction. Or to say the process repeats itself, and that's what a chain reaction is. But actually, you've said that. You've said that the neutrons released cause more fissions. That's what a chain reaction is. And last one then, explain, this is decoding, how a nuclear fission reaction in a nuclear power station is controlled. Plan, we just need to memorize that. What is it that we need to do to stop that chain reaction from happening? We need to catch those neutrons in some way. So our answer, the first mark, we absorb the neutrons. And we do that using control rods made of carbon or boron. But in fact, it's good enough in our specification just to talk about something that absorbs the neutrons will control the chain reaction. And lastly, that does not cause, so these are stopped from causing further fissions. Or you could say this stops the chain reaction. Now, why is chain reaction appropriate for that mark? Haven't they told us that? Well, no, they haven't. They've told us how a nuclear fission reaction is controlled. They haven't asked us, they haven't given us the word chain reaction. So importantly, we've demonstrated to the examiner that we do understand what we're talking about. We do know that this is a chain reaction and that that it can be stopped by absorbing the neutrons. Right, ladies and gentlemen, thank you so much for bearing with, and well done for having a look through this. I'm sure that you will do really, really well in your mock exams. Mock exams are super important periods of time. Any questions, then please do get them in there now. Put your faith in the light just had a question and deleted it so before I could read it. But if you do have one, then please do ask in the chat just now. If not, that is me. I've chatted for an hour-ish now. I will be back with more content in this live form in January, where we will talk about preparing for paper 2 mock exams. If you are watching recorded, I know quite a lot of you will be, so thank you very much indeed. Swifu, good to have you here. If you are watching this recorded, then please do leave a comment if you have any questions as well, and I will try my best to answer those comments, or I will actually sort of feed them into later things as well. Been like to do. Good, I'm glad they're helpful, Max. Yeah, it's just like a lesson, isn't it, buddy? So the other live streams for you to go back and have a little look at. Excuse me. I did how to revise and also practical questions in the first one, and I did calculation questions in the last one, and I did written questions as well. Round Bagel says, are GCSE 2022 going to be easier? No, the actual exams won't be any easier at all. What will be the case, we currently think, is that the grading curve will be slightly more lenient on you, and there will be probably more there'll be more grade 4s and 5s, and there'll be more of the higher grades than there was way back in the last exam series that there was, which was in 2019. But there will be probably a little bit less than was awarded by teachers in the last 2 exam series. So what's going to happen is generally grades are going to work their way back down to pre-pandemic levels. So if you think about like pre-pandemic level grades were about here, okay? During the pandemic, overall grades have gone up a bit. Then we're gonna, this year, probably be a little bit lower, next year a little bit lower again, and then next year a little bit lower again. Back down to the kind of level of pre-pandemics, okay? Good question. Yeah, do check out the previous live streams, Swifu, as well. They're good, they're hot. There's loads of stuff on my channel as well. There's loads of stuff on my channel as well. Playlists for every single unit in GCSE Physics and A-Level Physics as well. Somebody's asked there, how hard is it to get grade 9s for triple sciences? It is hard, nobody's going to lie to you about that, my buddy. But you can do it. What you need to make sure you're doing is practicing until you make few mistakes. Practice until you find it quite straightforward. And that comes down to doing as many questions as you possibly can. I do think revision is just about questions. We're talking about this so often. When you're young, when you're first revising for exams, the tendency is to think what I need to do is to write stuff down. I need to make notes, okay? But actually what that turns out to be is like just copying down from videos, copying down from from textbooks, and that doesn't help. It takes far too long as well. So what you need to do well is to actually answer questions. So find some good questions in a textbook, find some exam questions, blast through questions, blast through any multiple choice quizzes you can get your hand on. Yes, we are going to get equations for your exam. Okay, so if your school is not planning on giving you the equation sheet for your mock exams, then they should be. Because you're going to get them in the real thing, so do pester them if they've told you or they haven't said that yet. Somebody else asked a nice one, and you'll be told what comes up. Yeah, there is going to be some advanced information. They say it might not be that some things won't come up, but they might give us some hints. Like there will be a focus on this practical. There will be a large question on this topic area, so revise that. So there'll be more hints. You'll know a little bit more about what's going to be in the exam than normal. And how many hours of total revision did it take for grade 9? Well, that's a good question. It's not like there is an answer to that, okay, because it does obviously depend on the different people. But what I would say is don't think about revision in terms of time, but think about it in terms of tasks. So if you do a lot of self-quizzing, like maybe you've got a pack of flashcards, then if you work through that flashcards set once, it might take half an hour to work through that set of flashcards, right? But then once you do it, and the next time it might take 20 minutes, and then the next time it might just take 10. And then actually you might decide, well, I'm going to whittle that down to only the 5 that I really struggle with, and that might take 3 minutes to go through those last 5. But by doing that kind of process, you've gone really you've gone really quickly through a lot of material. And so, but the actual tasks you've done is a really deep and meaningful task. Okay, think about it in terms of, right, I'm going to sit myself down and I'm going to do 3 exam questions. So don't think about how long that takes. Like, great, if you can get those done nice and quick, then that's brilliant, that's wonderful news. Rather than thinking I'm going to do an hour of revision where I just copy out the textbook and really then do a test on that and get really disheartened when I don't do any better on that test. Right, I'm glad. Well done, C2 Eja, however you say that name. It's been nice spending time with you all. I'm going to go and hoover my house. No, I'm not actually, but I will see you all again real soon. Do just leave comments if you ever want anything on the videos, and I put out posts. And if you've got requests at any point, then do that. Yeah, that's a good idea to revise in the order of the mocks. Hopefully that was helpful in the order of the mocks there. And the question, how do I make a coherent set of flashcards? The best way to make a set of flashcards, in my opinion, is to look at the stuff you're supposed to remember from the spec or from the textbook and make them as question and answer. So, maybe have learn an objective from the textbook, answer to that learn objective on the other side. So it's really just like that. What's Yudoka Fintelman's method, Sweefy? I do like his channel. I think his channel is brilliant, actually. He's got a really lovely personality, hasn't he? And he's really focused, and somebody that we should all aspire to be more like. Really good to see how focused young people are on their exams. So I'm really pleased. So what's their method? Oh, you're revising topics out of order for the mocks. Yeah, fair enough, yeah. That's called interleaving what you're doing then. You're actually just skipping backwards and forwards and doing different topic techniques. In the first one, How to Revise, I talk about the top 5 revision techniques, and 3 of the top 5 are spaced, interleaved, and retrieval practice. And that's the stuff that you must be doing, those 3. If you're not asking yourself quiz questions, if you're not spacing your revision out, so leaving big gaps between them, between coming back to each topic, and you're not working through different topics, then you're ignoring some really key evidence. Anki's brilliant. And a Notion timetable, yeah, fair enough, good. But what I suggest you have in your timetable is not, I'm going to do this topic then, but rather than this topic, I'm going to do this thing. I'm going to whiz through my flashcards. I'm going to answer some exam questions. I'm going to do a past paper. I'm going to do physics topic on this. So don't think to yourself, I'm going to spend an hour revising chemistry. I'm going to spend an hour revising maths, but keep a list of the things you want to do in that time, and then just go and do those. Right, that's me. Thank you so much for spending the time with me. It's I hope it's been useful. If it has been useful, then tell your buddies, share it out as well, and I will see you all in January for some more live streams. I'm imagining your schools will do more mock exams and do a paper 2 mock exam, because all schools do the same things in January. Right, sounds like okay. All right, nice one everyone, see you soon.